Okay, in the last class, I show you that how to derive the tangential stress and longitudinal stress of a cylindrical pressure vessel. So what did we found? We found longitudinal stress PR by 2T. We can write sigma L equal to PD divided by 4T. Okay, this one. Then also we found tangential stress sigma T equal to PD by 2T. So these two formula is only valid for a thin wall pressure vessel and for cylindrical pressure vessel. This formula is not applicable for spherical or thick wall pressure vessel. So how we figure out that a pressure vessel is thin wall or thick wall? So you will get this one. Ri greater than 10 times T. If Ri greater than 10 times T, that means that pressure vessel is thick wall pressure vessel. Okay. Now, sometime in pressure vessel, say we are using a gas cylinder in our car. We are using pressurized cylinder in our kitchen. Those cylinder pressure is not that much high. But if you see that if you need extremely high pressure in the pressure vessel, then what need to do? You need to increase the thickness of the wall. If you look carefully, that sigma T is the most critical one, right? That is we put over here. So what did you see right over here? If thickness of the pressure vessel okay, sorry. So how did you see? If thickness, if you increase, that means sigma T will be decreased. So what does it mean? Say you design a pressure vessel and you found sigma T value, say for example, you got 70 KSI and you design with, so this one your value of sigma T. You design with steel 70 KSI. So your sigma T, you have to keep less than yield strength. Say yield strength of steel, just for example, you use this special steel and you found that yield strength equal to 68 KSI. You found yield strength equal to 68 KSI. So what did you see from here? You see that your pressure vessel will immediately fail because your tensile stress, that means obviously it is tensile, you put inside, but tensile hoop stress or circumferential stress or tangential stress become higher than yield strength. So your design is failed. Now, how we can fix it? You increase the thickness, right? So you increase the thickness, then your yield strength, your stress sigma d might be come down, say 60 kSI. Then you are safe because the tangential stress become less than the yield strength. Now, sometime you might have to design a pressure vessel with extremely high pressure. Then you need to increase the thickness more. So what is the problem? If you increase the thickness more in the pressure vessel. So this is the pressure vessel. So you increase the thickness more. If you increase the thickness more, then what will be happen? If you increase the thickness more, nothing wrong. Okay. But how pressure vessel made? If you look in your gas cylinder in your car or in your home, you are able to see this is the pressure vessel, and along lengthwise there is a welding. You'll see along this point there is a welding going throughout the length of the pressure vessel. So if this is the length of the pressure vessel, right, like this one, and you see there is a welding. And this welding also the inside to right of it. So how they make it normally? What they do, they take a sheet metal sheet, then they roll it. After roll it in a machine with a roller, and obviously you have to apply some pressure, and you roll down that one. Then this flat plate gradually converted into a round shape, and finally it becomes completely round. Okay, then you can do the edge, you can do the welding. But what is the problem? In our country, you see those pressure vessel cylinder might be thickness might be 4 or 5 millimeters, but sometimes pressure vessel thickness about 2.5. Especially, I worked one program on body of rocket. Okay, that was space mission, and it was made with 2 half cylinder. So you have a like this one. It has a certain length. Okay, body of a spaceship. Then is upper half like a cylinder. So what they'll do, they put together, then they put over here some joint and attach to body. That would be a complete pressure vessel. And this thickness we found about 2.5 inch. So 2.5 inch thickness mean that is huge thickness. 2.5 inch. Okay. So what I see, this rolling is extremely complex and expensive, and especially in US and Europe, they have a certain limited company. Say within US, there might be 10 or 15 company only able to do this rolling because it is extremely expensive. So after rolling, so especially I work in this pressure vessel. What we did, we buy the plate, and those plate we send it to other companies. So they roll it, then send it to my company. Okay, but after about 1.5 months, when we check the dimension of the plate, then we see the radius is increased. This plate. So what happened? You roll down to this way, okay? But material try to go back in initial shape. So we try to move along this direction and try to go flat. And over the time, its radius is increased. Okay. So what we did, we send it back to company again. They did the annealing, heat treatment, then roll it again. Okay. So what I'm saying, this is very expensive and also complex. For that reason, what need to do sometime, it is better to make, instead of using the huge thickness, you can use 2 cylinder. You have 1 cylinder, you have this one inside. That means there are 2 layer of cylinder. So this is outer cylinder, and this is the outer cylinder. You use the inner cylinder. Okay. So what is the benefit of it? Benefit of it, say a total thickness right over here, say for example 1.5 inch total thickness. Okay. So this thickness is 0.75 inch. And inner one you make 0.75 thickness. So it reduces the cost. Okay. And reduce the complexity. But if you keep the radius, how will fix the radius? So I can say this radius, this inner radius, right? And this is common radius, and this is outer radius. Now, if you keep this radius, common radius is same for both cylinders. That means for inner cylinder, this will be outer radius. And for outer cylinder, this will be inner radius, right? If both are same, then what happens? You can let me show. So this is your pressure vessel. In that case, you can put other one inside easily, right? Easily you can put it. But if you pressurize, then what will happen? There will be slip of the material. This cylinder might be slip at the common surface because there is no interference. There is a just loose pipe, loose fitting. For example, a smaller pipe, you just put inside of a bigger pipe, and then it's pressurized. If there is no interference, then it will move along this direction. Okay. So to prevent that, what we can do, you can say this is your outer cylinder. So it obviously it has a inner radius and thickness. Say for example, this is his inner radius. And this inner radius, say for example, I am putting 24 inch. Now I am taking this is outer radius, outer cylinder. Now taking the inner cylinder. Inner cylinder is outer radius. This radius, I can put it like 24.005. Then what will happen? This one you try to put inside of this one. So then what will happen? This is 24.005, a little bit bigger than this height. Okay. So this is bigger than this one. Then this is bigger than this one. Okay. So if this is bigger than this one, then you cannot put it. You have two options. You can hammer it a little bit, but if you hammer, then there will be micro crack developed right over here. You might cannot see in your eye, or it might say crack in the outer. Okay. So you have other option that you can heat the outer cylinder, warm up. If warm up dimension increase, then radius will be, diameter will be increased a little bit. Then you put this one inside. You put this one inside, then you just pull down to room temperature. Then what will be happen? Then they will be hold tightly together. Okay. So in that case, say you see my hand, I'm holding tightly, right? So inner cylinder, its diameter bigger than my outer cylinder, right? So inner cylinder try to push the outer cylinder outward direction, right? And outer cylinder will push him down. So that's why they will hold it tight. But between the common surface, it will generate some pressure. This is, I just draw it, seems like an egg, right? So this is two cylinders. Let me stick mouse here. This is your cylinder, outer cylinder. This is outer cylinder. This is inner cylinder. Okay. Then inner cylinder, this common surface, there will be some pressure. That is called contact pressure. So how do we happen? If I draw the outer cylinder, this outer cylinder, if I draw, then contact pressure will generate out of it. He'll feel a pressure from inside, right? And inner one, this is inner cylinder, who will feel pressure from the outside. From the outside. Just I try to hold my hand. What will happen? So if this hand made of steel and have higher diameter, I'm pushing, then what will happen? He will try to push me, apply pressure right over here in the outward direction. If this hand is strong, then what will happen? He will apply pressure around this inside of this hand. Okay. So there will be a common pressure, but both pressure, if this one is 100 psi or 100 megapascal, this will be 100. That means this contact pressure will be same. Now, how we figure out the contact pressure? It depends on interference. We keep interference point 0.005 inch, right? Then you can put interference point 0.01 inch. If you increase the interference, the contact pressure will be more. So right now there is no inside pressure. There is a contact pressure, then you put gas, then there will be inside pressure. Okay. So when we apply the interference, there will be contact pressure. If you put too much interference, then contact pressure will be too high. In that case, the crack might be developed right over here. Also, crack might develop right over here after assembly. So you need to make sure the interference should not that much, and contact pressure also not that much, right? But you know that there is a benefit if you put some interference. Benefit is that you can apply more pressure inside. Okay, so we will discuss it later on. Now I'd like to show you something that you have a pressure vessel. This is not pressurized. So after pressurize, what will happen? The radius of the pressure vessel will increase. Okay, so you will see initial pressure, the initial radius Ri, but final radius will be how much? It will increase little bit, right? So Ri equal to, we can say, R plus delta R. So this is R and this is RF. That means radius. Final radius Ri plus delta. I should put R delta. Okay. And initial radius is R. So when radius increase, what happens? The peripheral length of the cylinder is increased. Peripheral length means this much length is increased. So this much length is how much? 2 pi r. If you cut it right over here, if you make the straight in the both sides, then you will get length 2 pi r. So what will be initial length? 2 pi r into r. And final length will be pi r, pi into r plus delta r. This is your final length. So how much length increase? If you subtract this value, you get how much stress length, peripheral length increase. So peripheral length is P delta. This must increase. So what will be the peripheral strain? Strain will be delta by original length. So original length is delta P is the length increase, and original length is 2 pi r. This will be original. Okay. So from here, you can figure out the value of strain. You have the strain. Now you can figure out the sigma t. Why? Because we know Hooke's law, sigma equal to epsilon into E. And this strain is tangential strain, circumferential strain. So we can write down sigma t equal to ET, this value into E. Sigma t equal to delta P divided by 2 pi r into E. And from this relationship, we can figure out the value of delta R. How much radius is increase of a pressure vessel if you pressurize that pressure vessel. Okay. So let's see. That we discuss right over here. Okay, let's see how we can figure out. So if a pressure vessel is pressurized, is radius will increase by this one. Now we can figure out the increase in radius. Delta R equal to PR square divided by EP. Delta R equal to PR square divided by EP. So tangential stress in the pressure vessel equals sigma T equal to PR by T. Okay. Now, what is the peripheral length? Pi, initial peripheral length, 2 pi r. So after you pressurize, radius will be increased a little bit, right? So this radius we're thinking delta r. So what will be peripheral length? PF equal to 2 pi into r. R plus delta R is the final radius. So you will get this much, the final radius. So final peripheral length PF equal 2 pi into R plus delta. Now delta P equal to how much? PF minus PI. PF minus PI. 2 pi into delta R. You just subtract this value from this value. So this is the final peripheral length PF. This is the initial peripheral length 2 pi. So after you simplify the equation, your 2 pi R will be cancelled out. You will have 2 pi into delta. So 2 pi into delta R, this is the value. This is the delta P. Delta P mean this much length increase of the pressure vessel, peripheral length. So what is the peripheral strain then? Change of length divided by original. Change of length is delta P. The value is this one, 2 pi delta R, and initial length 2 pi R. So ET equal to delta R by R. Okay. So sigma T equal to this. Now we figure out the tangential strain or peripheral strain, and we know Hooke's law. We can add Hooke's law. Sigma equal to strain into modulus of elasticity. So we can say sigma T equal to tangential strain into modulus of elasticity. So we got sigma T equal to sigma T by E. Then this is your sigma T. We already know sigma T equal to this much. We already figure out, right? This is right over here. Sigma T equal to this much. So we put this value by E, and this value equal to how much? Delta R divided by R. Now this ET we are equal to delta R by R. Already we find it, right? So just put over the delta R by R. Then figure out the delta R. Delta R equal to P R square by E. So this much radius of the pressure vessel will increase after the pressure vessel. Okay. Okay. Now right over here, I have to told you that if you make a composite cylinder means you have a smaller diameter pipe, you put a bigger one. But there is no gap at the wall. Then what will happen? This will be sleeve little bit after pressure. There will be movement, right? So if you make the inner one little bit bigger, then you can hammer it, or you can, but people don't like hammer because after the hammering, there will be generate some stress or crack inside. But other option you have, you heat up the outer cylinder, radius will increase, then put the inner one, then pull down gradually, then hold it tight. But this one also people don't like because due to the you apply heat, material property change, thermal property, and it generates some thermal stress. They don't like. But normally, if you cool down the outer cylinder in a liquid nitrogen, like temperature minus 40 degree or minus 60 degree, if you cool down there, it will shrink little bit, right? Say inner one is higher diameter. Right over here is showing, I'm showing right over here that this is inner cylinder. This inner cylinder you put inside of this. Then what will happen? This inner cylinder, if you cool down in a liquid ice, then it will shrink. Diameter will decrease, then you put inside. Then keep it for room temperature for 6 or 8 hours. Gradually temperature increase, it will expand and hold it tight. Okay. So you see right over here that this is inner cylinder, outer cylinder, and how was the diameter of outer cylinder? Inside diameter this one. And the inner cylinder, you see inside diameter is from here to here. Now, this is inner diameter of inside cylinder. What is the outer diameter? From here to here. Now you cannot put it this one inside of this one, because this outer diameter is high. What is the variation between, or what is the interference? Interference you see is this mass, delta R. If I make a, you look over here, this figure is not completely right because this line has to be, this has to be outer diameter of the inner cylinder. Okay, but if you look the bottom figure right over here, this is the outer diameter of inner cylinder. Okay, and this is the inside diameter right over here of inner cylinder, outer cylinder. And actually what happened, like I am holding like that, like the inner cylinder, say you put in the liquid nitrogen, so it gets smaller and gradually come back to room temperature. So what will happen? Inner cylinder, it will expand. I mean, he will try to get bigger, right? And outer cylinder try to shrink him. Hey guy, don't push me. So after somebody try to pushing out, somebody try to pushing in, then they'll compromise each other. And finally, there will be a common radius. Because I show you already that after assembly, you will see that their radius is common. So you see right over here, I am saying if you think that this is the center line of inner cylinder and outer cylinder. So initially, this mass inner cylinder is that inner radius is this mass. But after assembly, they both are coming with a common radius line. The common radius line is this. So what does it mean? That means inner cylinder has to shrink that mass, delta Ri. And outer radius has to go bigger this mass. Then this one will go inside of this. That means after assembly, they will come down as a common radius. So how much inner radius shrink? Is radius decreased by delta Ri, and outer cylinder radius is increased by delta R. And this is called total interference. Total interference was how much? You see that this one is the point, inner radius of outer cylinder and outer radius of inner cylinder. So this distance is delta R. So this delta R equal to delta R naught plus delta Ri. So you see right over here, after assembly, the outer cylinder experience pressure from the inside, because inner cylinder try to go bigger, and inner cylinder, outer cylinder push him down. They say, hey guy, don't push me, better you shrink. So he pushing pressure from the outside. But both this pressure, this PI is same. Now we need to figure out this PI. How we can figure. Now you see, we found that initial interference delta R equal to DLTA delta Ri plus delta delta R naught. Okay. So now delta Ri we already delta R equal to P by R square Et. So delta Ri equal to Ri by Pi. Delta R naught, Ri, R naught, then T naught and E. So you see by this formula, we can easily figure out the interference speed, contact pressure. Say it was better to put one more line for you. I might not put it, but what I like to say that delta R. Delta R means initial interference. How much interference in radius between two cylinders. So this equal to, I can say, delta R of inner cylinder plus delta R of outer cylinder. If this value is given, this value say radius is 0.55, 0.055 millimeter. It's a 0.005 millimeter. So you have this value, then from the equation you put over here, we can figure out the contact pressure. So if you have the contact pressure, then from the value of contact pressure, you can also find the how much stress developed in this cylinder, how much stress developed in this cylinder, contact pressure. If due to the contact, if you put too much interference, then your cylinder might be failed due to the contact pressure. So you need to keep the contact pressure at a minimal level. Okay. So what is the time now? Anyone?
Sir,
How much time? 10:30 now. 10:30. Okay. Our class is 2-hour class, right? So I can give you a break 5 minutes. Then we'll start something else. Okay. Then we'll solve some problem. So you will come back at 10:36. Okay. Give me just little break. So top surface will be kind of sharp, right? Rectangular. This rectangular area you can calculate, then multiply by the pressure, you will get the force. Okay. So similarly, you have a sphere, that means a ball, football. You cut half with the knife. We cut half for knife at the center line. So how much pressure work along this direction is working? Sigma T. And obviously, your football is made of leather, but still it has a certain thickness, right? This certain thickness. So this area actually going all the way around. That means this area going actually like this. If I call the area like this area is like this. Okay. So this area you have working sigma T along this direction. So what is working in the left side? You see what is working force along this side? Along this side and this side, they are neutral by each other. Just side wall pressure is set. So how much pressure working along this side? How can you figure out? You press your hand from the right side. Bangla, chapter by your hand. What will happen? If I press this one with my hand, it will be kind of rectangle. So that area is the projected area. That projected area multiplied by pressure, you get the force. So projected area obviously should be a flat circle. An area will be pi r square. And if you travel in flying airplane, when you take the takeoff, if you look from the 45,000 feet, sometimes sky is clear, you can look to the ground and you will see all the roof is even. That means look like a flat surface. Though they are not flat. Some building is 50-story or 20-story, depending on the country and your location, right? But if you look at the top view, all them is in the same level. It seems like they are at the ground. So that is called projected area. Okay. So a building roof have, if you look, actually say some fancy people they make roof like that, incline. Say they look like incline like this. So how we calculate the pressure? So this is incline, right? This incline. You just make a rectangle with this one, septography. Okay, you press it right over here. Then this surface, this you will be matched with this one, then ultimately you will get a rectangle. That rectangle area multiplied by the pressure, you get the force. Okay. So anyway, right over here, what you see that if it's a spherical pressure vessel, then sigma T equal to PR by 2T. So you see right over here, this is sigma T and this is sigma L. So this is cylindrical pressure vessel. So you see sigma L coming half of sigma T. So sigma T is the more critical. For spherical pressure vessel, you see sigma T equal to this one. So these two is almost is same. Sigma L for cylindrical and sigma T for spherical. So what is the benefit of spherical pressure vessel? You have two pressure vessels. One is cylindrical, one is spherical. Both made of same thickness, same material. Inside volume is same. Which one you can pressurize more? Spherical or cylindrical? Anyone? Anyone? No? Obviously spherical. You see, in spherical you apply pressure, some pressure, it becomes head load. It's like sigma L. Okay. Half of sigma T. This equal to also half of sigma T of cylindrical pressure vessel. So what does it mean? That in spherical pressure vessel, a benefit that you can pressurize more. You can apply more pressure. What is the benefit? But what is the problem? Anyone guess? Nobody answered. So I can ask who? Asdik Chaudhary, roll number 102. You are here? Roll number 102 is not here. ID 99. You are here? 99? You are not here. Roll 18. Roll 18. Rion. Rion is here? Rion is not here. Okay. Rion, you are not here. But anyway, spherical pressure vessel, you can put more pressure, but problem to carry because it's difficult to support it because it's round shape like a ball, right? You need to support at the bottom. So that is the one problem. And some industry they use it, but most cases I see they are cylindrical shape. In rare case, I see in US in one city, they have a spherical water tank. And you can see from 10 miles far from the city, if you're driving around that city. Okay. So for fancy reason, they might put a spherical pressure vessel like one. Now, right over here, we are calculating the R, the formula. Formula is this one, like PR P equal to PR by T. So what is the radius, inner radius, Ri? So if calculating pressure, right over here. 1 second, you are calculating pressure right over here. If you use Ri, you can use pressure over here. That means if you use Ri instead of R, stress will be higher. Or you can choose right over here at the middle. So sometimes they put sigma T. Could you hold on 1 second? So what I'm saying, in some book, they instead of Ri, they use what is this much distance? Half thickness. They use Ri plus half thickness. But it don't make that much difference because in thin wall, respect to radius, wall thickness is very small. Okay. So this is the formula. Now we can solve some problem. Okay. And it's very simple problem. You look at before that, any do you have any question? No, no question. Okay. It's a steam boiler is 1.5 meter diameter. Internal pressure PI, internal pressure given 16 megapascal. Made of this much thick plate. Calculate circumferential, tangential, or longitudinal stress. So you see tangential stress sigma T and longitudinal stress sigma L. They'd like to know that. So what is sigma T? Sigma T equal to PR divided by T. And this sigma T, I'm sorry, sigma L equal to PR by 2T. So sigma L, that's too small. Sigma L is half of sigma T. P is given 1.6 megapascal. So if convert in 10 to the power 6 Pascal, diameter 1.2 meter, you put wall thickness is given 20 millimeter thick. So you can directly put over here. Okay. Obviously, thickness you convert in meter. Then you put the formula, you'll get a Newton meter square unit in pressure. So everyone understand over here?
Yes, sir.
Yes, sir.
Yes, sir. Okay, good. I appreciate your response. But did I make any mistake over here that I didn't mention? Obviously, I did. Because I write down this formula for thin wall pressure vessel. Right? But in the question, nothing mentioned that it is thick wall or thin wall. But we are directly choosing the thin wall pressure vessel. So we need to prove it. How we can prove it? You figure out the
Sir,
Ri.
the thickness is very small, so it should be thin.
No. You have to figure out this rule. If Ri greater than 10T, it obey this formula, then it will be thin one. If become this one, Ri less than 10T, then this will be thick wall. This is thick wall. That formula we can teach you. And this one thin wall, but we have to know it. Okay, we have to show it. So what is Ri? Ri is the, you can figure out in this problem, Ri equal to 1 by 1.25 divided by 2, come in meter, right? Then you figure out thickness, or you both one you convert in millimeter. Ri and 10T, that means 200 millimeter. Then you see it, then you mention that Ri greater than 10T, so this is a thin wall pressure vessel. Then you use this formula. Okay. Now we can see the second. Let me show you actually. No, in the form of when you solve, you write down, right? Given internal diameter this much, internal radius equal to diameter by 2 equal to how much? You write down the thickness of the wall equal to 20 millimeter, convert in meter. Then you write down internal pressure 1.6 megapascal equal to 1.6 into 10 to the power 6 Pascal. Then what need to figure out sigma T equal to what? Sigma L equal to what? Then you write down. Then you write down that you figure out 10T. 10T equal to 20 thickness into 10. Then compare with the inner radius. If Ri greater than 10T, then that is thin wall pressure vessel. Okay. So let's solve problem 2. Problem 2 is saying 20 millimeter diameter spherical tank. It's saying spherical tank, not the cylindrical. Used to be stored gas. The shell plating 10 millimeter thick. Shell plating means wall thickness. Working stress 1.25 megapascal. What is the maximum possible pressure will be in the tank? So let's solve this one. I can share this one. Okay. This one problem. This one is problem 2. So you see 20 millimeter diameter spherical pressure tank. So you write down internal diameter of the tank Di equal to 20 millimeter. Shell plating thickness 10 millimeter. Internal radius of the tank Ri equal to Di by 2 equal to 10 meter. Wall thickness 10 millimeter. So T equal to 10 millimeter. Convert in meter. It's a yield strength of the tank. What is saying? The working state of the material. That means you are using a material. That material can yield strength is that much. So when we apply the stress, what will happen? Apply the pressure, what will happen? The wall experience the stress. That stress cannot be bigger than 1.25 megapascal. You need to remember that. So that one is the yield strength of the material. So what is saying? For maximum possible gas pressure, P equal to how much? That we need to figure out. So at first, you write down what data is given, then you write down what we need to figure out. Then, you know, we teach you on the thin wall pressure, but still you need to prove it. If this is thin wall or this is thick wall. So I write down condition for thin wall pressure vessel Ri greater than 10T. So this is your Ri 10T equal to 0.1. What we found? Obviously Ri greater than 10T. So you write down, so spherical tank satisfies the condition of thin wall pressure vessel since Ri greater than 10T. Then maximum tensile stress in the spherical tank sigma T equal to PR by 2T. So sigma T, we found this much. No, sigma T we didn't found it, right? They know how much pressure you can apply. That means you need to figure out the value of the P, but maximum sigma T cannot be more than 1.25. So you put the value of sigma T 1.25 right over here, then you solve it. T value is given, Ri, we know, we figure out the P, and we get this. T equal to 0.25 megapascal. Okay. Any question from this problem? Anyone? No question? Okay. Then we can see the problem 3. Problem 3 is saying a laminated pressure vessel. Laminated means 2 cylinder, 2 pipe put each other inside. It's a 2 thin coaxial cylinder. Coaxial mean what that mean? Obviously, their center line has to be same. That is called coaxial. In the state prior to assembly, that means you don't assemble together, you don't put together. The interference between 2 cylinders. There is interference between 2 cylinders. That means the inner radius of outer cylinder and inner radius of outer cylinder. That means this radius and outer radius of inner cylinder. That's my hand radius. There is a difference. This difference, it's a there is interference. The outer cylinder is heated, then placed on inner cylinder, allowed to cool. Both cylinders are made of same material, same diameter. After assembly, it's 100 millimeter. That means after assembly, common radius is same. Find tangential stress in each cylinder resulting from shrinking. Shrinking means from the contact pressure. If initial interference in diameter, that is diameter one is bigger, is 0.25 millimeter. The thickness of inner and outer cylinder are this much, 0.25 millimeter, 0.2 millimeter respectively, and E equal to 200 gigapascal. The laminated pressure vessel of 2 coaxial cylinder, mean diameter of assembly D 100 millimeter, and this D equal to 0.1 millimeter. Mean radius of assembly, we figure out the radius. Wall thickness of outer cylinder, convert in the meter. Wall thickness of inner cylinder, convert in meter. Now interference field is given in terms of diameter, but our formula has in terms of radius. So we convert in radius. That means diameter divided by 2. This much is the interference. And also saying both cylinder made of same material. So it's a value of E is given. So for both cylinder, E equal to 200 gigapascal. This is this much gigapascal. Now, this is our formula, tangential stress formula. But we don't know how much the contact pressure. If you know contact pressure, you can apply that formula, you can figure out. Now, total interference is given. We know the diameter, how much radius increase or decrease after pressurize. You can pressurize from outside, radius will be decreased. Pressurize from inside, radius will be increased. That value you can figure out by this formula. So for inner radius, this much radius will be increased. For outer radius, this much radius will be for decrease, right? So right over here, our value is given delta R. So this delta R equal to this value plus this value. Okay. So we just put this formula. Now this Ri, both cylinder has its same common radius same after assembly. So if I draw the circle, say this is outer cylinder, this is inner cylinder. So what happened? This thickness, this is a common radius. This is R. Okay, and that common radius is given over here is 100 millimeter. Common radius. The problem. Right over here. Mean diameter of the assembly 100 millimeter. You convert in diameter in meter. So you can figure out R we figure out 0.05 meter. Then we have this formula. Put it over here, put it over here. Then instead of Ri and R, both will be same. right? For outer cylinder, we take Ri. That means this one. For inner cylinder, you take Ro, right? For inner cylinder. So Ro equal to also R. Then you see, just rearrange the equation. You figure out the, and this P value is same. Just figure out the P value from this equation. Outer thickness you know, inner thickness you know, R is given, delta are given. Easily you can figure out the P. So this is value of P. This value of the P is at the contact surface. That means right over here. Right over here, outer cylinder filling pressure from inside, and inner cylinder filling pressure from outside. So now you just use the formula sigma T equal to PR by T. This is T naught we put represent the outer cylinder. This is Ti represent the inner cylinder. So we got this one. Okay. This is stress on the outer cylinder. This is stress in the inner cylinder. This stress is not due to the fluid pressure. Remember, this stress is due to the interference in the contact pressure. Then again, if you put some fluid inside, some air or some chemical inside, there will be a pressure inside over here. And if the stress, this pressure and contact pressure, then need to summarize. But that one we learn in the machine design when we study the equal pressure. Okay. So any question? Anyone didn't understand or have any question? Anyone? No?
No, sir.
So we can leave it here.
Yes, sir.
Okay, so thank you very much. And our
Sir.
exam.
Yes, sir. If you tell us the time of the exam, that would
Okay,
be.
I like to take it on Saturday because I'm not able to take it in the weekday in your class time because a huge syllabus. Still, I have 3 more chapter. I have to finish it. So, what about the Saturday? Whatever time you choose is holiday, right? You can choose about night 10 is okay. I give you a 2 hour or 1 hour time. Might be a couple or one problem. Then you.
Sir, I think it would be better if you take the exam after 2 p.m. maybe 2
After
p.m.
2 p.m. Okay.
But our CR will notify you about the exact time.
The time. Okay. Then you
will notify you.
okay. So what I'll do, I look in the you'll get very short time, but like little bit higher time to upload the file. Okay, but you will not get that much time to share the information to each other. But when you look your script and we see that somebody mango, write down mango. By mistake, somebody write down mango, B, and everybody write down mango. So that's make your result, your number going down. That means obviously you're copying. So don't do that. Okay. You might say, okay, sir will not study, sir will not look at it, and he will not understand. He will understand easily. Even I give you all the scripts. Okay, Mr. X, you check those scripts, sit down in my room and give the number. You will understand that these 3 guys is copying each other and everybody writing back. You understand? So don't do that. Okay. So your CR tell me to contact with me so we can fix the time on Saturday. 2 syllabus is torsion and the column. Okay.
Okay, sir.
Okay. Thank you.